Beginning with this video from 3.4, we're going to examine some problems where we're now solving logarithmic equations. In order to do this, we first, if it's a basic equation, we would like to just use the one-to-one property, which really just means when I get to a point where I have log equals something, remember the statement that a log equals an exponent. That's what we're going to use for those. If it's not basic, then we need to get all of the logs together on one side and all of the constants or numbers on the other. And then we need to eliminate the logarithm after we've written it as a single log. So you put them all together on one side, create a single logarithm using logarithmic rules, then raise both sides to the power of the log base. So if it's natural log, we use e. If it's log base 5, we would do 5 for both. And then solve the remaining equation and check for extraneous roots. So what that tells us is that in some cases, we're going to get x's that cause the interior of the logarithm to be outside of its domain. So we have to remember that if we have the log, natural log, 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 whatever, of say x, then x has to be greater than 0. So if we get a negative answer for the argument on the inside, that's an extraneous root and it's not a solution. So let's take a look at a few of these. The first here is log base 2 of 3x minus 1 is equal to 5. This is a basic logarithmic equation. So we're going to use the fact that a logarithm equals an exponent. The base is 2, and the exponent, right, is what it equals. That's 5. So it's 2 to the 5th has to equal what's inside the log, which is 3x minus 1. So we're doing nothing more than just using the definition of logarithm there. 2 to the 5th is going to give us 32. Then I'm going to add 1 to both sides here. So I get 33 equals 3x. This looks like it's going to turn out really nicely. Divide by 3 on both sides. And I get x equals 11. Now I just have to prove that that works. So I'm going to substitute that back in. So log base 2 of 3 times 11 minus 1. That's going to be log base 2 of 33 minus 1, which is log base 2 of 32. Now 32 is 2 to the 5th, so log base 2 of 2 to the 5th. And remember, if we have log base 2 and inside of the argument is a base of 2 to a power, well, then we just get back the power. So it looks like we get 5. So that one worked out just fine. Let's continue here with another example. So this time we don't have the log isolated already. So that would be the first thing we would need to do. So I'm going to subtract 1 from both sides. And I have 2 log base 3 of 2x plus 3 is equal to 4. Divide both sides by 2. So I have log base 3 of 2x plus 3 is equal to 2. Now, once again, we have a log equals a constant, so we can use the fact that a logarithm equals an exponent. And so this tells us that 3 squared has to equal the argument of the log, which is 2x plus 3. 3 to the second power is 9. And at this point, I just need to subtract 3 from both sides and get 6. And divide by 2. And I get x is 3. All right, so let's plug it into the original and make sure that it still works. So we have 2 log base 3 of 2 times 3 plus 3. Let's just say equals 6. Right, it's okay if I move the 1, or sorry, equals 4. It's okay if I do it correctly, right? All right. So 2 times 3 is 6. 6 plus 3 is 9. I have 2 log base 3 of 9. We know that 9 is 3 squared. So I have 2 log base 3 of 3 squared. 3 squared inside of a log base 3 just becomes the exponent. So we get 2 times 2, and that is indeed 4. So it does look like that works out as well. So I'm just going to remove this so I can continue on with the next example here. All right. We have another nice basic equation. We just have to isolate the log, and it's not too bad. We just have to divide both sides by 3 in this problem. So we get natural log of 2x is equal to 4. And then we use that first bullet point that it said if we have log equals a constant, remember that the log equals an exponent. Now remember, for natural log, it is base e. So another way we could actually think about this, and let's just make this the first time we do it, let's assume we didn't know this was basic. In order to get rid of the logarithm, I would raise both sides by base e. And in doing so, the log and the exponential cancel, and I just get the argument 2x on the left, and it equals e to the 4th on the right. Then to continue solving for x, I would just need to divide by 2, and this looks like it's my final answer. And as always, I need to plug it back in just to make sure that it works. So I have 3 natural log 2 times e to the 4th over 2 is supposed to equal 12. So 3 times natural log 2 divided by 2 cancels, and I have just of e to the 4th. And because natural log and e are inverse functions, they cancel, and I get 3 times 4, which is indeed 12. So it appears this guy works just fine as well. All right, continuing on, I have natural log of the square root of x minus 8 is equal to 5. There's a couple different ways I can do this. One that I can do is start off by saying that square root is the same thing as expressing this as 1/2 power. And then the 1/2 power can come down in front of the logarithm. Now, if I'm multiplying by 1/2 on this side, I could multiply through by 2 everywhere and get rid of that. And then I have isolated the natural log on that side. Then I'm going to raise both sides base e, and e and natural log are inverse functions of one another, so I just get x minus 8 on the left and e to the 10th on the right. Then I would just need to add 8, and I get x equals e to the 10th plus 8. So we'll plug that back in a second. Let's just look at an alternate way of doing this. Right at the beginning, I started with this. I could, at the beginning of the problem, raise both sides base e. So then I would get square root x minus 8 is equal to e to the 5th, because e and log cancel. To get rid of a square root, I need to square both sides of the equation. So that would be x minus 8, and on this side, raised to the 5th, then squared. You multiply those two together, and you get e to the 10th. And we're right back where we were. So there is a couple different ways you can do these, or at least certain ones. Let's go ahead and plug it back in just to make sure it works. So natural log of the square root of e to the 10th plus 8 minus 8. And that's going to give me natural log of the square root of e to the 10th. E to the 10th is e to the 5th squared. So that's, let's do square root e to the 5th squared, and square root n squared are inverse functions, so they cancel, and I get natural log of e to the 5th, and natural log of e is an inverse function, so I just get back 5. So it looks like that does work. All right, so these are, pretty smooth so far. So of course we got to make things harder. Here we have a logarithmic equation where there is a log on both sides of the equation. Notice that they are both the same base. So again, there's a few different ways you can do this. If you like, I'll show you both ways. So because they're both the same base, at the beginning of the problem, I could technically do 6 raised to both of these powers. And 6 raised to the log of base 6 cancels. And at that point, I just get an algebraic equation. That's pretty easy to solve. Right, I just get the arguments are equivalent, which makes sense. So let's finish solving this. So I'm going to subtract 3x here and subtract 3x there. Then I'll subtract 4. It looks like I get x equals negative 19/4. Okay. So let's look at a different way of solving and see if we get the same thing, and then we'll just plug it back in and make sure that it works. So another way I could have started the problem is what the bullets tell me to do, is to get all of the logarithms on the same side of the equation. So I could do log base 6 of 7x plus 4 minus log base 6 of 3x minus 15. And that would equal 0. All right. I have 2 of the same types of logs, which means that and they're subtracted, so I can put them together. So this is a single logarithm of base 6 of 7x plus 4 divided by 3x minus 15. And this equals 0. To get rid of the log base 6, I'd have to raise both sides of this equation by base 6. So if I do that on the left and on the right, on the left, these cancel, and I get everything on the interior, which I have been calling the argument. And on the right, I have 6 raised to the 0. So anything to the 0 power except 0, of course, gives us back 1. So if I then were to, say, multiply the denominator to the right side, I would get myself back right here. So just an alternate way of doing it. Let's go ahead and see if this answer is viable now by plugging it in. So I have log base 6, 7 times negative 19/4 plus 4 is equal to log base 6, 3 times negative 19/4 minus 15. So I can continue to evaluate these, or I can use the fact that the interior, right, the arguments of the logs have to be greater than 0. So just quickly to calculate that, I'll do 7 times negative 19/4 and then add 4. That's going to give me a negative 29.25. So that's not good, right? I can't have negative numbers in my log. And I don't even have to try the other side because I've already shown that it doesn't work here. So unfortunately for this one, no solution. Okay, let's continue on. So here we've got a combination of logs on the left-hand side. So the very first thing I would like to do is to put them together and make a single logarithm. Remember that if we add logs, then we can turn them into a single log of the interiors multiplied together. So this would be x times x minus 8. Right, so I just multiply these two. And then after I've done that, now I have that basic equation again, right? A logarithm equals an exponent. That means 3 squared has to equal the inside here, which is x times x minus 8. So that gives me 9. It's equal to x squared minus 8x. I have to go ahead and move the 9 over, set this equal to 0, and I'm going to have to factor. But it's not too bad. Right, this is x squared minus 8x minus 9 equals 0. Now I'm looking for two numbers that multiply to -9 and add to -8. Those should be x minus 9, x plus 1. Solving those for x, I would get x equals 9 and x equals -1. The 9's pretty simple, right? If I plug 9 into this one, it's fine. If I plug 9 in here, 9 minus 8 is a positive 1. Where I get my problem is the x equals -1, right? The second I plug that into this first logarithm, the interior of that log is a -1. And so that's not allowed, right? The inside of the log has to be greater than 0, which means this guy is not a solution. And this is my only viable solution. So this is where this comes out the most often, I would say, is when you end up with quadratics and things like that inside, or that you get out of the logarithms, right? We all know that a quadratic equation has two potential solutions. In this case, one of those solutions was not also a solution to the logarithmic equation. All right, I think we have a few more examples here. So this time we've got a combination of logarithms, all same base, which is good. So I think what I'm going to do is I'm going to put the two logarithms on the left-hand side together. And the way that I can accomplish that is using a logarithmic rule, which says I can just multiply their arguments since they are added. And once I've done that, now I have a log of base 2 equals a log of base 2. And so I could raise both sides by base 2, and all of these would cancel, and it would tell me that the interior, or the arguments, now have to be equal. So pretty quickly, I can reduce this down to just a pretty easy algebra problem, right? This is x squared plus 2x. Let's get everything on the same side. So I'm going to subtract x and subtract 6 on both sides. So I get x squared plus x minus 6 is equal to 0, because everything over here canceled. I need a factor, so two numbers that multiply to -6 and add to +1. Those should be x plus 3 and x minus 2. If I solve those, I get x equals -3 and +2. I would need to know if any of those are extraneous roots. Very quickly, I can tell that the -3 is not going to work because I had a log in the beginning of the problem that had a single value of x, and log base 2 of -3 is not allowed. And so I can tell that this is not a solution. Then if I plug 2 in, right, I get 2 here, I would get 4 there, and I would get 8 there, none of which break the rule of being less than 0, and therefore these are all okay. So it looks like my only solution in this instance is x equals 2. All right. Now we've got a combination of logarithms. They're all natural log, which means they all have base e. So once again, I'm going to take the 2 on the right-hand side and put them together as a single logarithm. So this is going to be x minus 1 divided by x plus 1. Right? If I'm subtracting logs, they can be made a single log but division. Once I have both sides are log, or in this case natural log, I can raise both by the base e. Log or natural log and e cancel, and I quickly get to this equation. Now that I'm here, I'm going to go ahead and move this to the other side by multiplying by it. And then I'm going to go ahead and FOIL. So I would get x squared plus 5x plus x, and then plus 5. Adding like terms on the left-hand side, I would have this. Then I need to subtract these, or subtract the x and add the 1. They all cancel on the right, giving me 0. And on the left, I have x squared plus 5x plus 6. That's a nice factorable equation. I'm looking for two numbers that multiply to equal 6 and add to 5. So that would be plus 3 and plus 2, which means x equals -3 and x equals -2 are my proposed solutions. And ironically for this one, because these are both negative, if you look at the second logarithm, right, it's natural log of x minus 1. Plugging a negative into there, whether it be -3 or plugging in the -2, results in a log of a negative number. And because of that result, it turns out that neither of these solutions are actual solutions to our problem. So they might work for the quadratic that we got from simplifying, but neither of these actually work for the logarithms. So there is no solution for this problem. And that concludes section 3.4 on exponential and logarithmic equations.